Welcome back. My name is Sanjana and I'll be explaining Chapter 5 of the Brain Facts book. This chapter is called Thinking, Planning, and Language. So I'll start by explaining the patient called DBM. He is a 72-year-old man and has suffered from many strokes. In the case, DBO was only able to identify 1 out of 20 objects by sight. But he was able to differentiate items when he was feeling them, with his eyes closed. He could also recognize sound. So this case helps the neuroscience because now we know about how certain areas of the temporal lobe are involved with recognizing objects by seeing them. So now let's talk about regional specialization. One example of this is the fusiform face area, and that's used to recognize faces, and damage to the fusiform face area is called prospagnosia, which means you can't recognize anybody's face, like even if you're really familiar with the person. The next thing that I want to talk about is the regions that encode for words that include these are like the posterior parietal lobes, parts of the temporal lobes, and regions in the prefrontal cortex. So the combination of all these regions and can help build a better understanding of concrete and abstract ideas. And it can be involved in relating certain words, for example, a day, week, and month, and you can see that these words are all related, and so this can build a better understanding of a topic. The fMRI is used to measure brain activity when word processing happens. So the fMRI is the functional magnetic resonance imaging, and this can measure brain activity, especially in the left hemisphere compared to the right hemisphere. Language processing. The visual word form area reveals connections between it and brain areas that process visual information. In France, a man named Louis Victor Laborge came to the hospital and he could only say the word tan. He became known as Patient Tan. The doctor who performed an autopsy found that he had an aphasia, a lesion in the frontal lobe. That area is now called the Broca's area, after the doctor who discovered it, Pierre Broca. The Broca's area is vital for speech production, and it's also called non-fluent aphasia. So this means that speech can be impaired, but comprehension can work just fine. So after Broca published this paper on patient tan, another similar case in Germany happened. So this time it was a patient called SA, and she could not understand speech. So when someone talked to her, the sentences that like she said back like when she responded, it did not make any sense at all. So if you asked her something about a specific topic, she would respond with something completely unrelated, and this is called Wernicke's aphasia, the damage of language comprehension. The Wernicke's area is really important for speech understanding. So now let's look at the image. So as I mentioned before, the Broca's area is in the frontal lobe, so you can clearly see that the blue area in this image is the Broca's area, but then the Wernicke's area is the region in the green. So now let's talk about the FOXP2 gene. So this gene encodes for the switches of the areas in the brain and it turns them on and off. And the mutations in the FOXP2 gene can result in jaw movement problems. So I'll give an example of a bird in this case. So much like in humans, birds can learn their songs from older birds. They imitate this in a special period called critical period for rapid development. And when the mutation happens in the FOXP2 gene, this can potentially disrupt learning in younger birds. And this can severely affect the basal ganglia, and which interrupts flow of information, resulting in speech deficits in humans. Now let's talk about the prefrontal cortex. So the prefrontal cortex is like the first one in and the last one out, and what that means it's like the last one to fully develop, and it's like the first one that starts degenerating. and it's fully developed in the late 20s, and it's very important in control. So it's like something from decision making to controlling impulses. And a specific region in the prefrontal cortex called the orbitofrontal cortex is important for situations involving reward and punishment. And the prefrontal cortex can keep information active or like in the mind when an animal is carrying out a task that depends on it. Executive function. Executive function is the blend of three core skills: inhibition, working memory, and shifting. First, let's go over inhibition. We can see this with a simple example in younger children, ranging from 3 to 4 years old. Lucia's hand game. This is when a child is supposed to show a fist when they're shown a finger, and vice versa. This requires the inhibiting of imitation of adults. 3-year-olds struggle with this activity, while 4-year-olds are more successful. People get better at activities that involve inhibition over time. The second part of executive function is working memory. This depends on both the prefrontal cortex and parietal lobes. If you can remember in chapter 4, working memory is like a short-term memory. This is like remembering a phone number without writing it down. It can seem simple at first, but after an hour or two goes by, you are more likely to forget this information. Finally, we can look at shifting, switching tasks, activating many areas of the prefrontal cortex. Take a card sorting game, for example, changing the way you sort the cards. People with a damaged prefrontal cortex can face great difficulty when doing this, but children can do successfully. That's the end of chapter 5. I hope you enjoyed listening to that chapter. If you haven't yet, go watch my other videos on the previous chapters, and I hope you can watch my video on the next chapter, chapter 6. Thank you.